Assalamualaikum warahmatullahi wabarakatuh. So we continue with chapter number 6, division. Okay, division. Okay, so we want to know uh, the protein or the virus or whatever molecule that moving in our blood, how it diffuse in our blood, or how fast it move from one part or one point to another point. Okay, so we want to develop the theory of division and Brownian motion. Okay, so this we start with the Fick's law. Again, we see in some of the even in advanced method we have this Fick's law. So the theory of division can be developed from the two simple and basic assumption. Okay, so here we say that a substance will move down its concentration gradient and it conserve the conservation of matter. Okay, so berapa banyak yang pergi daripada satu tempat ke satu tempat mesti sama initial number equal to the final number. Okay, so this the Fick's law. Okay, a substance will move down its constant gradient. Fick's first law saying that the amount of material passing across the point at x or through a unit area perpendicular to the direction of a flow per unit time equal to this equation. Okay, so these are the flux. Jx equal to minus d partial c over partial x. X is the position, d is the diffusion constant, j is flux. The minus sign means that the flow is in the direction of decreasing concentration. Ini macam contohnya tool lah, pondok tool. Okay, so we have the number of car passing the tool counter at a certain time. Okay, so conservation, then we have the conservation of matter. Okay, so from the initial part to the final part, so jx plus delta x minus jx dt equal to minus delta cx del x. Okay, the difference between the two flux jx and jx plus delta x determine how much material we accumulate within the region bounded by x and x plus delta x in a time interval delta t. Okay, so kalau kita ada satu compartment, keluar masuk that compartment, so berapa banyak yang masuk, berapa banyak yang keluar dan bergantung kepada masa. Okay, so the Fick's second law, jx plus delta x minus jx delta t equal to minus delta ccx. So delta j, this one is delta j delta t equal to minus delta c delta x. So this one is just rearrange. We have delta c over delta t equal to minus delta j over delta x. So equal to minus partial minus d delta cx dx over partial x. So you can see that we have this division equation. Okay, these are the division equation or the heat equation in our advanced method. So there must be a linear relation between the gradient and the flux, and the division substance must be conserved. Okay, so we have this division equation. Okay, and in the 3 dimension, okay, d over nabla squared c. So nabla squared is the Laplacian operator, partial squared partial x squared, then dz squared. Okay, so these are just the solution or the equation in our advanced method we can see. So if we have these are the diffusion equation and these are the initial value. So if we solve this diffusion equation with this initial value, so we are going to get this solution. Okay, so we can estimate Cx at x point. Okay, the concentration will be smaller and smaller after some time. Okay. Okay, and the solution for one dimensional division from a point. So the root means displacement from the initial position increase in proportion to the square root of the time from x squared integration of cxt. So these are the from our quantum mechanics expectation value or the average. Okay, so these are expectation value. So x squared equal to 4 dt. Okay, the root mean square displacement is equal to 4 dt. So these are distribution constant time the times. Okay, the times. Okay, so we can estimate how far this molecule move move in time, move from the initial point to the final point. Okay, macam kita ambil kereta lah, kita ambil kereta, memandu kereta tanpa tujuan. So kalau kita start daripada Kuantan, memandu ikut suka hati kita, so adakah kita sampai ke KL ataupun kita masih dekat lepas 1 jam masih dekat dengan Kuantan ataupun Indra Mahkota O UIA Kuantan. Okay, so this one we can estimate how long it will take the meteorite to diffuse through a cell when it's produced at one location. Okay, so each vector of 10 in time give a factor of square root of 10, 3.16 in the distance. Okay, so these are the distance, root mean square displacement. Okay, so this one is for the 3D, three-dimensional point. So here if we have this delta partial, this differential equation, okay, d1 over r squared partial dr dc over dr. So we have this solution. Okay, so this solution we have the initial value. So this solution for this initial value is this equation. So solving this root means displacement. So we're going to have r squared equal to square root of 6 dt of the root the displacement or the molecule movement, the movement of molecule from the initial position to the final position. So how how far it from the initial position. Okay, so this again across the interface. So we have the initial value. These are division equation, initial values. We solve this, so we are going to have this solution. Okay, so this one is from our environment method again. Okay, and solution across the interface again. So this one cx dt. So if we take the initial x prime 0 to infinity, so we have c naught over 2 error function c minus x square root of 4 d. Okay, so we can set x, these are x, and this the time. We know the deviation constant, and we know the initial concentration, so we can get this type of graph. So after time it will be the same for each side, x minus or x plus. Okay, solution for division with a boundary condition again. So this one again our environment method. So using this division equation, initial value and boundary condition, so we are going to have this solution. Okay, so we can plot the solution. And again and again, this one division boundary condition. So initial value, boundary condition from our environment method again. So we are going to have this equation. Okay, so the concentration at each point will decay as the sum of many exponential. Okay, again and again, so we have division boundary condition. So we have this initial value, the boundary condition. So these are the solution for this division equation. Okay, so this one, if we plot again, we are going to have like this. After some time or t approaching infinity, so we are going to have the same concentration for each compartment or each side. Okay, diffusion at a steady state. Okay, so when dcx over dt equal to 0, so no, maknanya jumlah yang masuk sama juga jumlah yang keluar. Okay, so we are going to have the Laplace equation. Again, this one is from our advanced method. dc over dt equal to d nabla squared c. So nabla squared c equal to 0. Okay, so we have solving this. Integrate once, integrate twice. So c naught t c l t c naught. Cx equals c naught over l. J equal to minus c naught d over. Okay, so g total equal to this solution. Okay, so we can get this diffusion constant. Again, and we see that a small hole. So if we have a small hole, so we have this Laplace equation. So we have CRT minus A over R plus B. R approaching infinity, T 0, T equal to 0. So CRT equal to RA C naught over 2R, and the flux will be J equal to 2 DRA C naught over 2R squared. Okay, so RA is the radius for the small hole, R squared is the radius for the radius of the molecule. So we have this. Okay, so you can see this. Okay, so the flux through any hemispherical shell T equal to pi RA DC naught. Okay, so kalau kita ada circle dekat bulatan tu, so the flux through this hemispherical shell is equal to this pi RA D. You know, this RA is the diameter of the cell, pi is the pi j, so d c naught. Okay, so what we can say is that the rate of transport is proportional to the radius of the hole rather than its area. Okay, radius of the hole RA, and diffusion through hole transport is limited by the approach to the hole rather than the passage through the hole. Okay, so it depends on the diffusion. Okay, so how fast the molecule arriving at the hole. Okay, ataupun kalau dalam contoh tool tu berapa cepat kereta tu ataupun lori tu sampai ke pondok tool. Okay, so it doesn't care about the width or the berapa besar pondok tool tersebut. Okay, so depend on this diffusion. So here is steady state solution for a porous membrane. If there are N4, then we get a rate of transport. So kalau yang ni tadi contohnya satu pondok tool. So ini kalau kita ada banyak pondok tool. Okey. Tempat tool yang besar tu banyak laluan. Okey. So this one also we have a N4. Okay, so we have T porous equal to, or the membrane have N4 or N channel. Okay, so we have N pi RPD C naught. Okay, so if the 4 are small compared to the entire hole, the 4 will cover only a very small fraction of the total area of the membrane, but still give the same flux as the open hole. Transport would be greater than the unobstructed hole. Okay, so macam contohnya pondok tool lah. Kalau satu pondok tool saja, diffusion dia ataupun pergerakan dia kurang kereta yang boleh melalui dia. Tapi kalau banyak pondok tool, so lebih banyak molekul boleh passing at the same time. Okay, so a porous membrane, when more pores are added, the crowding of the cell make T porous equation less accurate because of the overlap of the pore, but give T over T naught 1 over 1 plus pi RA NRP, where the T not the rate of transport for the arm struck hole, T equal to N equal pi RA D C not. Okay, so here kalau terlalu banyak point dot tool pun boleh menyebabkan the flux becoming smaller, or the passing car will be much smaller because of this bertindih. Okay, so that is this overlap 4. Okay, so there are two let's say two tool box. Okay, that one or two molecule trying to enter. Okay, so it will be much smaller. So what we want to say here is that more pore is good, but there must be a limit of number of pore for the membrane. Okay, so if not, then the flux will decrease. Okay, so diffusion at steady state. Okay, so the conclusion: a few pore can have a large impact on how quickly a solid cross cell membrane. And cell membrane can harbor many different types of membrane transporter and allow the selective passage of many different kind of molecule. Okay, so here we can see that by having this hole or different pore size, okay, different for or different channel, so a different molecule can pass through that channel. Okay, so contohnya macam again the tool box or the tool, ada khas untuk lori, ada khas untuk kereta, ada khas untuk touch and go, ada khas untuk RFIDs, ada touch untuk smart tag. Okay, so allow a different selective passage, different kind of molecule. The transporter for each molecule only need to occupy a small fraction of the membrane surface area. They will not crowd one another. Okay, so these are for the membrane. A cell membrane can thus transport many different substance efficiently. Okay, so depend on the size and the attraction, so it can move. The ion can move freely from the membrane. Okay, so that's for the part 1.